We tend to think of physics as this incredibly complex thing, right? Blackboards just filled with equations. But really, it's just the secret set of rules that governs absolutely everything around us. So in this explainer, we're going to pull back the curtain and uncover some of that hidden physics in the world you see every day. And we'll start with a really simple question.
Okay, so think about this. You've definitely seen it happen. You dip a paintbrush in some water or paint, and the bristles all splay out. But the second you pull it out, bam! They all snap together into a point. What's going on there? It's not glue. It's not some kind of weird magic. It's a fundamental force of nature doing its thing.
The answer in 2 words is surface tension. The best way to think about it is to imagine the surface of the water is like a thin, invisible, stretchy skin, and the skin is always trying to pull itself together, to shrink and take up the least amount of space it possibly can. So when the brush comes out, those little films of water between the bristles contract, and they pull the bristles right along with them.
So why does water have this stretchy skin? Well, it all comes down to something called cohesive forces. That's just a fancy way of saying that water molecules really like to stick to each other. On the surface, the molecules don't have any other water molecules above them, so they get pulled inwards by all their neighbors below. And that inward pull is what creates the tension, that powerful contracting force that clumps the bristles together.
It's pretty cool, right? And that same principle of internal forces applies to solid objects too. So let's take a look at the physics behind all the everyday things that stretch, bend, and bounce right back into shape.
The big concept here is elasticity. It's the property that allows a rubber band to snap back after you stretch it, or a ruler to bend without breaking. Honestly, it's a material's built-in desire to go back to its original shape after you've pushed it or pulled it around.
Now, to really get a handle on elasticity, physicists use 2 key ideas: stress and strain. It sounds complicated, but it's not. Stress is basically the force you're applying, like how hard you pull on that rubber band. And strain is just how much the object deforms because of that stress. So how much the rubber band actually stretches. The relationship between the stress you apply and the strain you get is what tells you exactly how stretchy or stiff a material is. Okay, I know this slide looks a little technical, but the core idea is actually super simple. It's just showing an experiment to measure that stress-strain relationship we were just talking about. Scientists will take a beam, apply a very precise force, and then carefully measure how much it bends. This gives them a number, called Young's modulus, that tells them exactly how strong a material is. And for engineers building things, that number is absolutely crucial. So why does all this matter? Well, take a look at a steel I-beam, the kind that holds up buildings and bridges. That I shape is no accident. It's pure physics. See, when a beam bends, the biggest forces, the pulling and the squishing, happen at the very top and the very bottom. So engineers cleverly put most of the steel there and just use a thin piece in the middle to hold it all together. You get maximum strength with the minimum amount of material. That's physics in action, literally holding up our world.
All right, let's switch gears. We've talked about static objects, but now let's get into things that are in motion. Specifically, let's dive into the absolutely fascinating physics of what happens when things spin.
This is such a fantastic way to put it. We all get that mass is how much an object resists being pushed in a straight line, right? It's just inertia. Well, for things that are spinning, there's a rotational version of that, and it's called the moment of inertia. Put simply, moment of inertia is an object's rotational laziness. It tells you how hard it is to get something to start spinning, or, once it's going, how hard it is to stop. But here's the key part. It doesn't just depend on how heavy the object is. It also depends on how that mass is spread out around the center of the spin.
And this idea leads to one of the most beautiful and elegant laws in all of physics, the conservation of angular momentum. All it says is that if you have a spinning system and no outside twisting force or torque is acting on it, its total amount of spin has to stay the same. It's a simple rule, but it has some truly incredible consequences.
Just think of an ice skater or a ballet dancer doing a spin. When their arms are stretched out, their mass is spread out far from the center, so their moment of inertia is really high. That makes them spin kind of slow. But then watch what happens when they pull their arms in tight. All of a sudden, their moment of inertia drops like a rock. And to keep that total angular momentum constant, something else has to shoot up, and that something is their speed. They start spinning way faster, almost like magic.
And this is where it gets absolutely mind-blowing. A planet orbiting the sun follows that exact same rule. As it travels along its oval-shaped path, it gets closer to the sun at some points. When it does, its moment of inertia relative to the sun goes down. So to conserve angular momentum, it has to speed up. The very same law that makes a dancer spin faster is what governs the dance of the entire solar system.
And speaking of planets, let's zoom way out and talk about the force that's orchestrating this whole cosmic ballet in the first place: gravity. This, right here, is Newton's world-changing idea of universal gravitation. It's elegantly simple. It says that every single speck of matter in the universe pulls on every other speck. The bigger the objects, the stronger the pull. And this is the really crucial part. That pull gets weaker as the objects get farther apart. Not just weaker, but much weaker, dropping off with the square of the distance.
Now, the funny thing is, long before Newton explained why planets move like they do, an astronomer named Johannes Kepler had already figured out how they move. Through years of just painstaking observation, he came up with these 3 laws that perfectly describe their motion, from their elliptical paths to the exact timing of their orbits. Newton's law of gravity was the missing piece of the puzzle that finally explained why Kepler's laws worked.
Here's a little misconception a lot of us have. We learn about g, the acceleration due to gravity on Earth, and we think of it as this constant number, but it's not. If you go up a mountain, you're farther from the center of the Earth, so gravity gets a tiny bit weaker. But what's really wild is that as you go down into a mine, gravity also gets weaker, because now you have some of the Earth's mass above you, pulling you up.
Okay, for our final topic, we're going to move from the pull of gravity to another invisible phenomenon that literally shapes our reality: waves.
You know, the fundamental building block of any wave you can think of is a simple back-and-forth wiggle. It's called simple harmonic motion. If you picture a pendulum swinging or a weight on a spring bouncing up and down, that's it. It is the purest, simplest form of oscillation, and it's the foundation for everything from the sound you're hearing right now to the light you're seeing with. So when these little oscillations start to travel, they form waves. You have progressive waves, which are what you'd probably picture, like ripples in a pond. They carry energy from one place to another. But then you can also get what are called stationary waves. Think about a guitar string. When you pluck it, the wave is basically trapped between the 2 ends. It just vibrates in place. That's a stationary wave, and it's a way of storing energy in a vibration.
So, what can we do with all this? Well, we figured out how to generate sound waves with frequencies so incredibly high that our ears can't detect them at all. These are ultrasonic waves, and because their wavelength is so tiny, they have some really incredible properties that we've learned to use in amazing ways.
And this is where it all comes together in the modern world. Just by understanding how simple waves work, we've developed technologies that sound like they're straight out of science fiction. We use ultrasonics in sonar to map the deepest parts of the ocean. We use them in hospitals to see inside the human body without making a single cut. We can find microscopic flaws in airplane parts and even use them to perform surgery without a scalpel. All of that from understanding a simple vibration.
From a paintbrush to a planet, it just goes to show how much incredible physics is happening all around us, just beneath the surface of what we can see. So the question I want to leave you with is this: if these are the invisible rules we've managed to uncover so far, what else is out there? What other fundamental forces might be shaping our reality, just waiting for us to discover them?